path-independent vector fields have a very nice property that when you integrate them along different paths connecting the same points, the result will be the same. In this example, you are walking up from the origin to the point 0, 4, 4 through 3 different paths while you are exposed to the gravitational force field. We will find the work done onto you by the gravitational force field in these 3 scenarios. When we find the parametrization for the line segment, we will use the formula t times endpoint minus starting point plus starting point to get the parametrization. We have t times 0, 4, 4 minus the origin plus the origin again, and thus the parametrization is 0, 40, 40. The velocity vector is 0, 4, 4, the derivative. This over here we will denote r of t, and this is r prime. In this path, t will range from 0 to 1. Now we should evaluate f at the parametrization. However, f is constant. So we are just left with 0, 0, negative mg. This calculation won't be repeated. But then we take the dot product and we get f of r dotted with r prime, and this is 0 times 0, 4 times 0, and 4 times negative mg. This is negative 4 mg. Finally, we integrate. The work is the integral from 0 to 1 of the resulting dot product. But this is just negative 4 mg. Please hold this result in your memory. For the circular path, I will give you the parametrization. You do not need to know this. The way that we parameterize the circle occurring from 0 to 0, 4, 4 in the y equals c plane, you can see that this is an inclined plane, unlike the ones that we're usually accustomed to in the xy plane. That circle can be parametrized via this function. Here t will range between pi and 2 pi. Once again, the specifics of this parametrization are not necessary to be known. The velocity is the derivative of this path. And once again, evaluating f. In this case, just because it's constant, we're good, so we don't need to. The dot product of f and the velocity vector is 2 times mg, the sine of t. because the negative cancels with the negative from the negative mg. It happens that when you integrate this function, we get the same result as we got before. Observe that the integral from pi to 2 pi of the quantity 2mg sine t dt is 4mg. Sorry, negative 4mg. Why is it negative 4mg? The way I think of this is that when you graph the sine function, each lobe has an area of 2, but we're integrating the second lobe of the function right here. It has area 2 still, but it's below the x-axis, so it has area -2. Observe that this result matches the previous result of negative 4mg, so that's one indicator that our paths don't affect the result of the integral. Finally, for the sinusoidal path, we have that the parametrization is sine of pi t, t comma t, with t ranging between 0 and 4. The specifics of this parametrization are once again not necessary. The velocity is the derivative of this parametrization, which is just pi times cosine of pi t, 1, 1. Taking the dot product leaves us with negative mg. Because our vector field, remember, is 0, 0, negative mg, so multiplying by the last coordinate leaves us with just negative mg. We now integrate to observe the same phenomena as before. This integral runs from 0 to 4 of the dot product dt. This is negative 4mg. Please observe that this quantity is once again the same. What we have shown is that the vector field, the gravitational vector field, is path independent, as we have integrated from the origin to this point, 0, 4, 4, and have found that the work is independent of the path.